The Helmholtz energy gives us a way of determining spontaneity if our process is held under constant temperature and volume. And it's very convenient for that purpose. But we know that actually a lot of the processes that we might be interested in don't necessarily have constant volume, but they do have constant pressure. So let me draw an analogy. Earlier we saw that when we had internal energy, and we had a constant volume, there was an association there. For example, du could be related to Cv at constant volume dt. Similarly, there was a similar kind of association between enthalpy and pressure, where dH might be written as Cp dt, all things being equal for an ideal gas. So is there a similar kind of relationship that we can find here that allows us to distinguish another thermodynamic potential that might tell us about spontaneity other than the Helmholtz energy? Well, let's start once again with our familiar first law expression that the differential of internal energy is just the incremental change in heat and incremental change in work, and we'll once again identify this change in work as minus PdV. But for the incremental change in heat, we're interested in spontaneous processes. So I'll remind you that one of the results that we got when we talked about entropy was that the entropy, the incremental entropy, was always going to be greater than or equal to the change of heat when it's not specified to be reversible. So in other words, we could associate this increment of heat as being less than or equal to TdS. Now, I realize that we're used to thinking of it being equal to TdS, but for a spontaneous process, it won't necessarily be equal because we'll have an irreversible heat change. So now when I include this in my expression for du, I can plug in that minus PdV is what I'm getting for work, but if I put in TdS for dq, what I'm going to have to put in here is a less than or equal to sign for the internal energy. All right, but this is already telling us something about spontaneous and spontaneity in a process. Okay, because we know that this inequality sign actually is related to that spontaneity. So let's rearrange all of this, and we would now, in the same way that we did when we developed the Helmholtz energy, we would write this as minus TdS plus PdV is less than or equal to 0. But now I'm going to impose constant temperature and pressure. So in other words, that tells me that S dt is 0 and V dP is 0. So both of these are going to be equal to 0. So if I just arbitrarily add those in here, I could have that du minus S dt, which is 0, minus TdS, which may not be 0, plus PdV plus V dP, which is 0, will still all be less than or equal to 0. But this whole thing that I've written out, this big long mess, is just the differential, the total differential of U minus TS plus PV. So now I can use all of this to define for myself a new state function. I will call it G, and this stands for the Gibbs energy. So in other words, my criterion for spontaneity is going to be that the differential of this new state function, Gibbs energy, must be less than 0. That is, the change is less than 0. So this is very similar to the Helmholtz energy because, again, we're talking about a thermodynamic potential that's going to seek out a minimum. That's where it's heading no matter what. Okay, and that minimum is represented by when the Gibbs energy change is no longer negative. It's equal to 0. Okay, but it can never be positive because positive is going to move me away from our equilibrium position, which is written down here. All right, so this, as it turns out, is going to be actually a key thermodynamic quantity for us. Because it takes place under constant temperature and pressure, it applies to a lot of the kinds of reactions that we might run in a laboratory. Now, I'll note also that this thing down here, U minus TS plus PV, can be organized in different ways. For example, U plus PV is just equal to H. So H minus TS is this same thing. I also might indicate that, let's see, U minus TS, this combination of things, is just equal to the Helmholtz function. So the Helmholtz function plus PV is also equal to the same thing. So all of these actually are going to be equivalent to this new Gibbs energy that we've just created. So depending on what we want to calculate or the ease of calculating it, we could use any of these three expressions as a representative for the Gibbs energy. In general, we tend to favor this one just because it is the simplest, and there's sort of a symmetric analogy to the definition for the Helmholtz energy. So we might write, for example, that a change in the Gibbs energy is a change in enthalpy minus a change in the product of temperature and entropy. Okay, but in practice, we could use any of these things to make that association. Now, another relationship, and I'm not going to derive this, but I want you to be aware of it. We showed that the Helmholtz energy was related to the reversible work. Is there a similar relationship that we can exploit for Gibbs energy? In fact, there is. It's not quite as straightforward as the Helmholtz energy relationship, but the Gibbs energy, it turns out, is related to something I'll call the external work, which is all of the work except for PV work. So it could be electrochemical work, it could be magnetic work, but it also must take place under reversible conditions. So in effect, what we have is that the change in Gibbs energy is always going to be less than or equal to this W external, this other work, whether it's electrochemical other, when it's not done under reversible conditions. So this is the relationship. So this leaves us with a kind of an interesting set of associations that we can make between the various thermodynamic potentials. So I'll start with U and H. U, for example, could be set equal to the heat under constant volume, the heat exchange under constant volume. The enthalpy was equivalent to the heat exchange under constant pressure. The Helmholtz energy was equivalent to the reversible work, the total reversible work. And G is equivalent to the reversible work, and I'll call that external, so non-PV work is what this is equivalent to. So we can see that each of these thermodynamic potentials has an association with one of these interactions, either with heat on the case of internal energy and enthalpy, or with work in the case of the Helmholtz energy or the Gibbs energy. I'm actually not going to do very much with that, but I think it's useful to know, and it helps us to organize in our minds exactly what the roles of these different thermodynamic potentials might be. We're going to have more to say, much more to say about the Gibbs energy, because that's going to be the key thermodynamic potential that we'll deal with actually for the rest of the course.